The last video we set up the framework for inference for one mean. We noticed when we were talking about hypothesis test, our multiplier was no longer z star, we had this t star. And then similarly, for the hypothesis test, we had, instead of z-calc for our test statistic, we called it t-calc and said we would find the p-value associated with that using t-CDF instead of normal CDF. So we're going to pause for a few moments and figure out what this t-distribution is, why we're making this switch. So you see down at the bottom here, your name, the student t-distribution, has some interesting history here. It was developed by William Gossett. And he developed this while he was working at the Guinness Brewery in Dublin. And you might want to think about this, for the normal distribution, the sampling distribution to be normal, we said we needed a decent sample size for that central limit theorem to kick in, at least 30, maybe more. But maybe he's working at a brewery, maybe he has small sample sizes. He can't sit around and wait for the central limit theorem to kick in with a big sample size. So he worked on developing some methods to deal with small sample sizes. So just to give credit here, I took these from Wikipedia. Here's our lovely William Gossett. And you'll notice on the right, this is a picture of the t-distribution. And it looks a whole lot like the normal distribution. In fact, you'll see in our key here, our standard normal is this solid line here. So this is just the regular normal distribution, that normal CDF z-score stuff we've been using. And you'll see that the rest are the t-distribution, and they look kind of the same, bell curve centered at 0. The thing that's different is there's more room at the tails of the t-distribution, more room out here. This allows a little leeway if we don't have a huge sample size and maybe the central limit theorem hasn't quite kicked in yet to be fully normal distribution. So the amount of tails determined in the sides depends on our sample size. So the bigger our sample size is, the closer and closer and closer this goes to the normal distribution. Those of you that have had calculus before, this n goes to infinity. This t-distribution converges to the normal distribution. So if you have a small sample size, you notice in the key up here, this is a sample size of 3, which is going to give us the definition for how much area needs to be out here, called degrees of freedom. And it's calculated as n minus 1. So again, if n is 3 in this first line, then our degrees of freedom is 2. And that tells us how much, that we're going to have quite a bit of area out here. But if we have a bigger sample size, n of 10, our degrees of freedom would be 9. And we don't have quite as much area out in the tails. We don't need as much wiggle room. So maybe somewhere on here, write this note to yourself, degrees of freedom defines how much extra room we have out here compared to the normal, and our formula for that is n minus 1. So let's see how to find this on your calculator. If you got this with the normal CDF, should be pretty straightforward. We're going to go a little bit out of order. Let's start at the bottom of the page. So suppose we have our alternative hypothesis is less than, so okay, this picture basically looks the same. Here's 0 in the middle. Our negative 2.4 is over here. And because HA is less than, my p-value is the area less than. So to find this area, or this probability, you're going to use t-CDF on your calculator. The first two inputs are going to be exactly the same as you had for normal CDF. You're going to input your min and your max, your lower and your upper, but then you also need to tack on degrees of freedom to let your calculator know how much wiggle room you need in the tails there. So in this case, our p-value is going to be t-CDF. Our lower is negative infinity, so put whatever your favorite big number is, up to our upper of negative 2.4. And the last part that's different, we need our degrees of freedom. Since n is 20, our degrees of freedom is n minus 1. or 19. And if you work that out on your calculator, maybe pause, give it a try. The TCDF, by the way, is in the same place your normal CDF was. Just scroll down a little bit. You should get 0.0134. All right, let's try the next one together. So here's my normal picture, or my, T picture. This looks same as the normal. Here's my test statistic they give us of negative 1.2. HA is greater, so we're going to shade above our test statistic. So our p-value, because we're on the setting of means, not proportions, we're going to go TCDF for means. Our lower this time is negative 1.2. Our upper is all the way out to positive infinity. Again, just plug in your favorite big positive number. And we have that third thing we need to tack on, our degrees of freedom. So our n in this case is 23. Our degrees of freedom should be 22. And if you work that out, you're going to get 0.8785. All right, last one, just so you have an example of each case here. Here's our t-distribution, our test statistic of 2.9. Our alternative is not equal to, so I want to find the probability being not far away above my hypothesis, my null hypothesis, or below. So this is my two-sided test. I need to find one of these sides and double it. This is symmetric, so it doesn't matter which side you find. So I'll say p-value is equal to TCDF, and maybe I find the lower end, so negative infinity up to negative 2.9. You're also welcome to do 2.9 to positive infinity. You should get the same answer. Our degrees of freedom, n minus 1, should be 29. So that gives us this lower tail. We need to make sure to double this to get both sides because our HA was not equal to. When you do, you should get something like 0.0071. All right, so that's for finding p-values using the t-distribution. Exactly the same as the normal, with the exception of this third parameter we need to add of our degrees of freedom, n minus 1. All right, confidence intervals, we need to find the multiplier. So for confidence intervals, we're going to do this two ways depending on your type of calculator. So if you go back to your calculator where you had TCDF and normal CDF, take a quick look. See if you have inverse T. Nearly everyone should have inverse T. If you do not, I'll show you in a moment on how to find this using the T table. But for right now, I'm speaking to those of you that have inverse T on that menu of your calculator. And we're just going to do it much the same way as the normal distribution. We just need to add that extra value for degrees of freedom. So for normal, remember we had 95 in the middle, in this case, and then that would leave 5% left over, or 2.5% on either side. So I could find this value by inverse T. I know a percentage. And if I put in 0.025, that'll give me this lower or negative T value here. So 0.025, but the T distribution, remember, is defined by that area in the tails, which can change depending on your sample size. Our degrees of freedom are 14 here, n is 15. Just like the normal, this will give you a negative number. Always report your multiplier as positive. So just a moment, bear with me. I don't have this one worked out. So 0.025, let's do this together. And I got 2.145. Okay. Let's try another one. I think you'll get the kind of the feel after that. So the next one, let's do this guy. Suppose I want to be 90% confident. Then I've got 90% in the middle. That leaves 10% left over, or 5 on either side. So if I do inverse t of 0.05, it'll give me this negative t star. So t star inverse t of 0.05, I need to define it by my degrees of freedom, so 34 in this case, by n minus 1. Take the absolute value, and you should get, let's see, 0.05, 34 degrees of freedom. You should get 1.6909. All right. I'm going to give you the value for this one. Let me work it out real quick, and then you can kind of try it out on your own and make sure you get the same thing. All right, so for this middle one that I kind of skipped over, I get 2.6800 if you round this. So try that on your own. Make sure you can get that one. All right, I'm going to take a moment and speak to the people that do not have this inverse t on your calculator. You will be provided with a t table if you do not have inverse t on your calculator, and that's shown on the next page in your notes. So on the next page in your notes, you'll notice the left-hand side has our degrees of freedom. So you know how to calculate degrees of freedom is our n minus 1. You're going to select the appropriate row for your degrees of freedom. Then you're just going to select the column that goes with your level of confidence. If you scroll down for a ways, you'll notice degrees of freedom counts by 1 until you get to about 30. Then after 30, it starts jumping around a bit, 30, 40, 50, 60, so on. So suppose you have a problem where degrees of freedom is maybe, I don't know, maybe it's 31. No, let me change it up. Let's make it 39. So if your degrees of freedom is 39, it's not on here exactly, it's between these guys. And it might be really tempting to say degrees of freedom is closer to 40, so let's just use 40. Instead, you should use 30 to be on the conservative side. So use 30. So if you flip back to your previous page in the notes, if you're using the table, if your degrees of freedom is between two rows, always go with the smaller degrees of freedom, not the one it's closer to, but the smaller number. So let's revisit a couple of these. This one was 95% confidence. Our degrees of freedom was 14. So let's check it out over here. Our degrees of freedom are 14. And we're going to go over to the third column because that's 95% confidence. So we get 2.145, which is exactly what we got on the calculator. If we check out our second example here, 90% confident, our degrees of freedom was 35. Degrees of freedom were 34. 34 is not on here. Our rule is use the smaller, so 30. So if you go over 30 to 90% confidence, that's our 1.697. And you'll notice when we use a calculator, we got something similar, 1.691. So if you use the table, there's a chance you might be a little bit off from what people are getting on the calculator. That's okay. We account for that. We understand that might happen. All right, this finishes our explanation of how to use TCDF and inverse T or the table to find our p-values and multipliers. The next video, we'll jump into an example.